The broadcast is now starting. All attendees are in listen-only mode.
Hi, everyone. Welcome to the Weeks 3-4 S2S webinar series. We are still waiting for our second presenter to come in, but we are going to go ahead and get started here. As many of you are aware, this monthly series is co-sponsored by the OAR Weather Program Office S2S program and the NWS OSTI Modeling Program. I'm Mark Olson from the WPO S2S program. We have two really good talks today, but before I begin, I want to point everyone to the webinar series website, and in fact, I will post the link to that in the chat right now. If you want to go there and take a look at it. On the site, you can find information on all the upcoming talks. You can add yourself to the mailing list, stay informed of the upcoming webinars, and you can also access recordings of past talks. And perhaps, very importantly, especially to us, there's a form available if you're interested in presenting in a future webinar and spreading knowledge of your work. We currently have spots available over the next few months. So we encourage you to consider giving a presentation. As we said, we hope this remains an informal presentation, an informal dialogue here of just to kind of spark collaboration and keep people up to date on what's happening and give you a chance to advertise your work too. So finally, if you have questions for the speakers during the presentation, there's a link in the chat there, and I'll post it kind of probably periodically throughout there too, just so it doesn't get lost, to a discussion document. And so you can post your questions there. We may have time at the end for some questions if we have time to unmute people and they can ask directly. But otherwise, any questions can be posted there, and the speakers will be made aware of this, and they can go in and actually answer offline if needed too. So as I said, today we have two presentations. First of all, we have Dillon Elsbury and Laura Ciasto, if hopefully I got the names pronounced right. They're going to speak about assessing the representation of the stratosphere-troposphere coupling in the GESS version 12. After that, we have scheduled to talk Kai Huang, who will speak about the QBO-MJO connection in subseasonal prediction system. So we'll go ahead and get started and turn it over to Dillon to start, and I will go ahead and make him presenter now.
Awesome, thanks, Mark.
And you should be ready to go to present your screen.
Cool. Okay, is that coming through on your end, Mark?
It looks great.
Awesome. So hi, everybody. My name is Dillon Elsbury. I work at the Cooperative Institute for Research in Environmental Science, and I work closely with members of the NOAA Chemical Sciences Laboratory. Today, me and Laura Ciasto, who's at the Climate Prediction Center, as Mark said, are going to be talking to you about a diagnostic toolbox we've been working on that assesses the representation of stratosphere-troposphere coupling in the Global Ensemble Forecast System, version 12 here. And so before going forward, I want to acknowledge everyone who made this happen. Zachary Lawrence, who's not here today, but Zach has been an absolute workhorse for this project. He's a member of CIRES, works closely with members of the Physical Sciences Laboratory. And then we've gotten oversight, guidance, and work from Amy Butler at the Chemical Sciences Laboratory, Judith Pearl at the Physical Sciences Laboratory, and Eric Ray, who's also a member of CIRES and works in the Chemical Sciences Laboratory. And so this project's actually coming to an end to some extent. And so our team would like to say thank you to the funders, the National Weather Service, OSTI Week 3-4 program, who made this happen, and some of the other collaborators who are listed on the bottom of this slide. Okay, let me go forward. Oops. Okay, awesome. So 3 goals for this project. One is to develop a diagnostic toolbox to assess stratospheric forecast biases and stratosphere-troposphere coupling processes and NOAA products, and then incorporate these tools into MET+. This part has been a fluid process, I believe, with some of the diagnostics, but not all incorporated. And so these diagnostics are largely centered around formulating new validation and verification metrics that can exploit opportunistic stratospheric information to improve 3 to 4 week predictions specifically. And I think we've done this, and I'll show you some of these diagnostics later. And we've been applying these diagnostics and metrics to the NOAA products, namely the Global Ensemble Forecast System version 12 here, but some of the UFS prototypes. And yeah, and I think they're suitable for application to more real-time products. So this slide, I really want to get across one point. It's beneficial for forecast systems to accurately represent the stratosphere. And so this busy schematic on the left, not busy to be insulting, but it has a lot of information made by my colleague Amy Butler and her collaborators in a chapter they worked on. And it's showing you all of the stratospheric processes, or many of them, that affect the underlying tropospheric circulation. And so each of the plots is a latitude pressure cross-section, the one on the left showing you the southern hemisphere, the one on the right showing you the northern hemisphere. And so we're going to actually look at zonal mean, kind of like these plots, zonal mean biases in GESS v12. And then we're going to move on to look at the representation of the quasi-biennial oscillation in the GESS v12 hindcaps. And so the QBO is an internal mode of variability in which descending and alternating easterly and westerly winds in the tropical stratosphere, they descend over time, repeating every 28 months. And the QBO affects the atmospheric circulation globally. And so it's very beneficial for forecast systems to have a good representation of the QBO in them. One of those cell connections is between the QBO and the tropics. And so we're going to look at the relationship between the QBO and the Madden-Julian oscillation in GESS v12. This will be shorter. I'm excited to see Kai's talk next. Then following that, we'll move to the extratropics, and we're going to look at some statistics on sudden stratospheric warmings in the GESS v12 hindcaps. And in general, polar vortex variability is coupled to the underlying tropospheric circulation. So strong or weak vortex events have an effect on the underlying North Atlantic Oscillation, which in turn affects the mid-latitude tropospheric circulation. So we're going to move forward then and look at the sensitivity of the NAO to the underlying polar vortex. And then Laura is going to come on and talk about the current and future status of the toolbox. Okay, let's go forward. Yeah. And so just because of time constraints, we're going to show you some, but not all of the tools in the diagnostic toolbox. But in this gray box here on this slide, you can see, I think, 9 or so tools, all of the tools, half of which we're going to cover today. Okay, so what data are we going to be talking about? So as mentioned before, version 12 of the Global Ensemble Forecast System, we're going to be using the 2000 to 2019 phase 2 hindcasts. Each has 11 members, and they last up to 35 days. This is the verification in GESS v12 reanalysis. I should have updated that. The reanalysis, I think Zach and I did compare it to GESS v12 reanalysis in many cases, but for the most part today, the verification is going to be ERA5 reanalysis, or CFSR if stated. I'll point those out. And then I'm going to show you 2 results on showing the UFS prototypes. So P5, P6, and actually some P7. And so these periods, the forecast periods here are much shorter, 2011 to 2008. 2 forecasts a month up to 35 days. And we'll get into those results very quickly. So yeah, let's do it. So the first thing I'm showing you here are the zonal mean biases that exist in the GESS v12 hindcasts. So these are zonal means. You have pressure on the y-axis, latitude on the x-axis. The top left plot is the zonal mean zonal wind bias during weeks 3 to 5. And the bottom left plot is the zonal mean temperature bias during weeks 3 to 5. These are for all December, January, February, March initializations, and the verification here is ERA5 reanalysis. And so what you see, if you look at the top left plot, that tropical stratospheric wind response, you have westerlies, a westerly wind bias in the middle stratosphere, easterlies in the mid-latitude middle stratosphere, and a 2 strong polar vortex bias, strong westerly bias at high latitude. And so for the most part, these wind biases can be traced back to biases in the temperature field. And so if you look at the bottom left panel, panel D, what you'll see is that you have a globally layered stratospheric warm bias. And in the high latitudes of the northern hemisphere, you actually have a polar cap bias. And so these 2 anomalies kind of poleward of 60 degrees north. Bithermal wind balance will require that you have to have a westerly wind anomaly superimposed between them. And that's what we see in that top left plot. You also get these cold upper troposphere, lower stratosphere biases that are actually relatively common in S2S forecast systems. So going forward, Here, panels B, C, E, and F, which I've just added, are set up slightly differently. So they also have pressure on the y-axis, but they have time lead on the x-axis out to 35 days. And so panels B and E go together, and what you see here is the zonal mean zonal wind bias at high latitudes, primarily between 55 north and 85 north. And you see the development of that westerly bias over time. It kind of comes in close to the initial conditions and amplifies over time. Concurrently, you have the cold polar cap bias that is probably, I'd say, primarily responsible for the zonal mean zonal wind bias actually come into the forecast and persist all the way through. If you move your attention to the right side, panels C and F, you'll see the tropical middle stratospheric wind biases. So we're averaging between 10 south and 10 north. And you actually have a westerly wind bias that's present in the initial conditions and amplifies throughout the duration of the forecast. And then in that bottom panel, bottom right panel, F, you see that globally layered temperature bias that's pretty much present from the start of the initial conditions onward. So, oops, sorry. Okay. And so one thing I want to highlight is that, and I said it already, these biases are relatively common in forecast systems. And so you can see that in this first paper cited here. This is an effort led by Zach Lawrence. I believe Amy Butler and Judith Perlwitz also contributed. And they look at these zonal mean biases amongst many different forecast systems outside of outside of NOAA models, and find that these biases are generally common. And then this figure in particular is in a manuscript that's going through internal review in the physical science laboratory now. And so I wanted to show these because these are two of the outcomes of this project. Now here, I'm going to show you some of the biases that exist in the UFS prototypes. So the left column is showing you the zonal mean zonal wind bias. It's shaded with red being higher than it should be and blue being lower than it should be. And then on the right, you have the zonal mean temperature biases shading, showing you the bias. For each plot, you have climatological values shown in black. And so focusing on the zonal mean temperature biases, these are during week 5 in the prototypes. And for P5, P6, and P7, one thing you'll see is that you generally have that globally layered warm stratospheric bias. Its latitudinal extent varies to some extent by prototype, but for the most part, it is a feature regardless of prototype. You also have the cold upper troposphere, lower stratosphere biases that are present in each prototype, although their magnitude slightly varies. And then you have actually in the prototypes a warm polar stratospheric bias. And biothermal wind balance, this actually attenuates, weakens the zonal mean zonal wind, and you have an easterly zonal mean zonal wind bias. And so for the most part, although there certainly are some differences, particularly this polar cap bias, you have the warm stratospheric bias and the cold upper troposphere, lower stratosphere bias also appearing in the prototypes as they did in GESV-12. Okay, so now having shown some of the zonal mean biases, I want to switch gears and begin talking about the representation of the QBO in some of the NOAA products. So this plot, you have the velocity of the zonal mean zonal wind, that's on your y-axis, and then time on your x-axis. And so we're looking at the 50 hectopascal tropical winds, and we should see the QBO signal, we certainly do. CFSR is shown in black, and then the prototypes are overlaid in blue, green, and orange, respectively, for P5 through P7. And then you have the GESV-12 overlaid in gray. So this top plot is going to correspond to day 7, 7 days after initialization. Then you have day 14, day 21, day 28. And the point that we want to highlight is that you generally at day 7 have pretty good clustering of the prototypes around the CFSR. In other words, the models are doing a pretty good job of simulating the lower stratospheric portion of the QBO variability. But as you go out to day 28, it clearly degrades. P5 and P6 actually had 2 strong of easterlies. P7 does fairly better, and GESV-12 is doing a pretty good job. And so this is not the best guess for any of the models. In general, models struggle to maintain the amplitude of the QBO. This happens with global climate models as well. And so if you're not used to looking at the QBO, I just wanted to briefly share this plot because this will give you a nice full snapshot of what it looks like. Each of these are a pressure on the y-axis, latitude on the x-axis cross-section. And if you look between 20 south and 20 north, you'll see the QBO signal in this top left panel with easterlies and westerlies above them. And then as you move through over time, what you'll see are the westerlies, easterlies gradually descend. and then repeat with easterlies, for instance, in panel I being in the lower stratosphere. And so if you look at the top right panel, panel E, this is us taking basically lower stratospheric easterly QBO and comparing it to the climatology. That's kind of what the model should represent, this type of variability. And so it's important to represent the QBO because it has global teleconnections, one with the stratospheric polar vortex, one with the subtropical jet, and one through the tropics. It's coupled, dynamically coupled to the MJO. We're going to show some results for that shortly. And so that was all kind of context to get to this plot. And so on the top left here, we're showing you the zonal mean zonal wind biases in color for guess V12 data for weeks 3 to 5. This plot has pressure on the x-axis and latitude on the x-axis and pressure on the y-axis. And so these are for our 50 hectopascal easterly QBO initializations. And so 50 hectopascal easterly QBO, the winds should look something like this as a deviation from climatology. You should have easterly sitting around 50 hectopascal. And so if you move your eyes back to this left plot, around the magenta line here, we're actually picking up a westerly bias. And so guess V12 is actually having trouble keeping the amplitude of the lower stratospheric easterly QBOs intact. Similarly, or actually opposite in sign, in the upper stratosphere around 10 hectopascal, the westerlies are too strong for our lower stratospheric easterly QBO initializations. If we go forward, you get different problems for our westerly QBO initializations. So in this case, you should have QBO westerly sitting around 50 hectopascal, and we're actually getting a negative zonal mean zonal wind bias here. In other words, the westerlies are too weak in the lower stratosphere, and the easterlies that are sitting aloft are actually also too weak. And so in general, yeah, guess is having trouble holding the amplitude of the QBO to some extent at weeks 3 to 5, but I think this is to be expected. These biases are something interesting. I want to understand these more going forward. When you take the difference between these two panels, you can see that you actually get these temperature and the black contour anomalies out at in the extratropics. And this is letting us know that there are actually biases in the QBO's mean meridional circulation as well. And this is something to consider because the mean meridional circulation is how the QBO communicates with the extratropics. And so now let's get into the MJO stuff. So to get it started, we have a schematic here from St. Martin and others. And on the left, you're looking at the kind of setup of a schematic of the MJO during lower stratospheric easterly QBO. And so during easterly QBO, what you have is a cooler tropopause, reduced stability. You can have more cirrus cloud development, and in general, the convective plume is more well developed, propagates slower, bigger. During westerly QBO, things change. You have a warmer lower stratosphere, reduced stability, which will reduce cirrus cloud formation, and generally have a lower amplitude, less well-developed MJO. And so we know these relationships exist in reanalysis, and we want to know, do the guess V12 hindcast capture these, and if so, at what leads? And so what I'm showing you here are the bivariate anomaly correlation coefficients. So that's that bottom left equation. And so we're comparing the real-time multivariate MJO indices from guess V12 hindcast to a verification set of RMMs, and the verification in this case is AIR5. And so we care about when B-core, the bivariate anomaly correlation coefficient, is greater than or equal to 0.5. That's kind of a somewhat arbitrary threshold used in literature for skill of your MJO forecast. And so what we're getting for our December, January, February, March initializations, if we define the QBO at 30 hectopascal, we're actually seeing 6 days more of skill for our lower stratospheric easterly QBO initialization versus our westerly QBO initialization, the difference between 27 days and 21 days. If you define the QBO at 50 hectopascal, however, which is far more customary in the literature, we're actually getting no difference, no statistically significant difference in MJO skill at all. And so this is actually a relatively common result, the one on the right. And we're kind of finding here, if you actually just change the definition of the QBO, which is, it involves a different lower stratospheric temperature and stability profile, you actually get more predictive skill. Oops, okay. So moving on to the next slide, we saw from that schematic that the amplitude of the MJO should be higher during easterly QBO background states. And so we want to see if guess V12 can have that feature. But first, I'm going to show you what this relationship looks like in the reanalysis. This is AIR5. I've looked at this also from guess reanalysis. It's very similar. And so you have amplitude of the MJO shown on the y-axis as a function of MJO phase on the x-axis. And black line is for all December, January, February, March initializations. And the dashed line is showing you the MJO amplitude for our easterly QBO initializations versus the dotted line showing you our westerly QBO initializations. And so clearly you see this huge amplitude difference, easterly QBO-MJO amplitudes always being larger than westerly QBO-MJO amplitudes. This is pretty similar regardless of how you define the QBO, 30 versus 50 hectopascal, although you do see some big differences in phase 6 to 7 that are sensitive to the QBO. And so in the hindcast, we actually get a fairly good result. So this is week 3 to 5. The QBO has definitely degraded at this time in the hindcast, but guess for sure sees that the easterly QBO-MJO amplitudes are generally higher than the westerly QBO-MJO amplitudes, kind of regardless of phase. However, I will point out that for phases 4 and 5, there's basically no sensitivity to the QBO regardless of how the QBO is defined. And I think a hypothesis at this point is that this is arising from the maritime continent prediction barrier. The model's having trouble keeping the amplitude of the MJO as it passes over the maritime continent during phases 4 and 5. But anyway, yeah, the fact that these signals are persisting at weeks 3 to 5 is pretty good. Okay, so now that we've done QBO and QBO-MJO, let's switch gears and we're going to get into the extratropics, talk about SSWs and the NAO really briefly, and then we'll get to the result summary. And so beginning with this top left plot, we're basically trying to assess how long can we predict SSWs in advance. So sudden stratosphere forming extreme events when the 10 hectopascal winds at 60 degrees north reverses to easterlies, and this initiates global or hemispheric scale changes in surface temperature and wind, and these can be actually quite persistent. And so a hit here is a successful forecast, and this is when 6 of our 11 GESV-12 ensemble members will include an SSW. And so what you'll see with the hit line is that they generally, degrade over time. And what we want to compare the hits with are the false alarms and misses combined. False alarm being you forecast an SSW that doesn't happen, miss being you should have forecast an SSW, you missed it. And so as these kind of errors, we'll call them creep up, they surpass the hits around day 14. And so day 14 is kind of when we have our predictive skill. The right plot is basically going to tell you the exact same result, but it's done in a different way, where we kind of look at the limiting case where only one of the 11 ensemble members needs to include the SSW. That's fairly easy for the ensemble members to reach. However, we want to compare this black solid line with the dashed line, which is summing up the incorrectly forecasted events, the events that include false alarms or SSWs that aren't going to happen. This skill lasts out to 13 days. So in general, we're seeing predictive skill of SSWs about 2 weeks in advance, which is on par with other forecasting systems. And so here, last result plot, I want to show you some of the NAO results. This top left plot is really just more for give you an idea of how we set up the bottom left figure. And so these blue dots are basically your strong vortex cases, and the vortex is close to 40 meters per second in the zonal mean. And these red dots are cases when you have a weak vortex. We define here arbitrarily as 6.6 meters per second. And so what other research has shown is that the NAO correlation skill scores are actually higher if you have a weak or a strong vortex relative to a neutral, or I guess in air quotes, a more normal vortex. And so we're definitely seeing this in GESV-12. During weeks 3, 4, and 5, you generally have higher correlation skill scores for your weak and strong vortex cases relative to your neutral vortex cases. And so in summary, we're going to have 2 summary slides. Kind of what I've shown you here is a snapshot, an evaluation of the GESV-12 subseasonal hindcast, focused on stratospheric biases, stratosphere-troposphere coupling, and some extreme events. And so in general, GES has similar stratospheric biases to other forecast systems. It underestimates the amplitude of the QBO. This is a relatively common problem. It's particularly strong in the lower stratosphere. And when we look at the MJO, we're actually getting far higher predictive skill of the MJO for easterly QBO initializations versus westerly QBO initializations. The difference is 6 days, and it happens when we define the QBO 30 hectopascal. We get more predictive skill of SSWs after 2 weeks, on par with other forecast systems, and higher predictive skill of the NAO when a forecast is initialized with a weak or strong vortex state. And so really briefly, on the bottom are 2 of the publications, one published led by Zach, and the one that's going to be kind of an overview paper of GES and some of these stratosphere-troposphere coupling things. We submitted the NAO and MJO reanalysis, ensemble mean, and all ensemble member indices to NCAI, so those will be public hopefully soon. And then all along the way, Zach was providing EMC with evaluations of UFS prototypes, some of which I've shown today. And in general, this project has produced a lot of scripts, the Python module and Toolbox scripts that can be used for successive model development. And so I went over slightly on time, I'm sorry, but at this point, we're going to transition to Laura Ciasto.
All right, thanks, Dillon. Hopefully everyone can hear me. My name's Laura Ciasto. I'm the point of contact at CPC for this project, but I'm also a week 3-4 forecaster at CPC, so I can really appreciate the relevance of these projects since we very heavily rely on the GEFs when making our week 3-4 forecast. So in my short 5 minutes, I just want to quickly mention CPC's plans for this toolbox, but also show some of the real-time forecast verification that's been updated at CPC. So as Dillon said, we do have plans at CPC to implement this diagnostics toolbox, or at least parts of it. And to give a little background, CPC has often worked with EMC to provide these stratosphere evaluations. So Craig Long, who has since retired from CPC, he provided the initial GEFS V12 evaluations as well as the GFS V16. So it does make sense for CPC to kind of continue on in this collaborative role. So the plan is to implement this diagnostics toolbox, but also continue collaborating with EMC. So we want to be able to prioritize the diagnostics and then also work with EMC to add additional diagnostics such as ozone, specific humidity, et cetera. And below is the schematic. Like Zach said, this project has produced many a script. So it's a matter of combining, adapting, automating where possible to kind of put it all together into this evaluation package. And we're aiming to have this ready for GEFS V13, GFS V17, if that's what EMC needs for us to do the evaluations. So next slide, please, Zach.
Sorry, Laura, here, 1 second. There we go.
So yeah, I'd like to spend the rest of the time just giving some quick updates on the real-time verification. And you know, real-time verification is important. We want to understand how these biases and differences that Zach showed in the hindcast are manifested in the real time and affect our ability to leverage the stratosphere in real-time week 3-4 prediction. So CPC does provide real-time stratosphere GFS GEFS forecasts. Graphics, but the real-time verification is limited. So we've made several updates. These are currently developmental, so they're internal, but EMC does have access and ideally they'll be made public down the road. I'm showing some of the GFS metrics here. One of the big things with V16 is it's been extended all the way up to 0.01 hectopascals. So we have graphics to include that. And in terms of verification, we're including the correlation and RMSE that are available for multiple levels at days 7, 10, and 14. So an example of this is on the right for zonal winds at 60 north at 0.1 hectopascal, and this is verification over the last 120 days. You can see we're plotting both the GFS analysis as well as the forecast. And then on the bottom, we have the RMSE and the forecast error growth. So we can see how these errors evolve as a function of forecast lead. We're also doing this for other variables and pressure levels, which I've got listed at the bottom. Next slide. For GEFS, one of the biggest updates we made here was actually just extending our forecast graphics to include leads out to 35 days. So we really want to encompass that week 3-4 period. We also want to include the individual members so we get an idea of what that spread looks like. So there's an example of that below. This is 10 hectopascal zonal wind at 60 south. And this gives you an idea of what the Southern Hemisphere polar vortex looks like right now. And this is an interesting time of year to watch it as the ozone hole over Antarctica is growing. And then similar to GFS, we've got the RMSE and the correlation plots on the right for the last 120 days. We've got the ensemble mean forecast, the F0 analysis, and then the correlation and RMSE. We also have some rank histograms. But with that, I'm going to stop. We're right at 2:30, 2:31. So I want to leave time for the next speaker to be able to present their work. But thank you.
Great, thank you, Dillon. Thank you, Laura. Very interesting. There is in the discussion document, I see Eugene put a few references there, and there's at least one question so far in that discussion document. And, in order to save time, I'm going to ask Dillon and Laura to just go into the document and answer within there. So we can go ahead and move over to our second speaker, Kai. And we did not get a chance to practice, make sure he can present, but I'm going to go ahead and make you presenter now, Kai.
All right.
And if you can go ahead and try to present your screen, you are a presenter. We can see the full window.
All right. Can you see my screen?
Yep.
So
And
which screen are you seeing? Because I have
yep.
two screens.
Yep, I'm seeing just the slides, so that's good.
Okay, that's good. Yeah.
Yep, full screen.
Okay. So yeah, I guess I will start. So the title for my talk will be the captured MJO QBO connection in a subseasonal prediction system. So this work was done in collaboration with Yagar at NCAR and my advisor Kathy Pigeon. So right. All right, yeah. So the QBO-MJO connection was first discovered in 2016, where two papers found that MJO is stronger and more likely to cross the maritime continent in the QBO east years and in the QBO west years. And such kind of differences are actually accounting for around 40% of the MJO interannual variation. So it is a very robust connection. And also, this kind of connection is found in the S2S prediction systems, as illustrated by this nice figure here. These are the operational S2S prediction systems around the world, and many of them actually capture the higher MJO prediction scale in the QBO East year than in the QBO West year, and several of them are actually very robust. So since the MJO QBO connection is so robust in the observation and provides so many scales in the S2S prediction systems, and people really want to know what are the responsible mechanisms behind it. And it is not an easy work. There are so many different theories proposed, and among them, there are two major theories. The first school of theory is called the high cloud theory, which people found that over the maritime continent, the high cloud is actually increased in the QBO East year than in the QBO West years, which may influence the cloud radiative feedback for the MJO convection, which is very crucial for its amplitude, and which may also influence the local diurnal cycle precipitation over the maritime continent, and then influence the eastward propagation of the MJO when the MJO convection is over the maritime continent. Another school of the theory is called the static stability theory or the Toolbox instability theory, where they found that the static stability around the tropopause is actually decreased in the QBO East years, so which may destabilize the tropopause and is favorable for the further development of the MJO convection. And there are actually two types of the tropopause instability they're focusing on. The first type is actually the equatorial zonal mean tropopause instability, which is directly related to the QBO phase. Like in the QBO easterly phase, it will generate a cooling around 100 hectopascal, which may increase the tropopause instability and makes the MJO convection become stronger. And another type of the tropopause instability they're focusing on is more in the MJO scale. Like people already found that for the MJO convection, it will induce a cooling around 100 hectopascal and warming around 200 hectopascal. So these vertical sections, the shadings are the temperature anomalies associated with the MJO composited in the QBO East years and in the QBO West years. You can clearly see such kind of high-level cooling and low-level warming structure is stronger in the QBO East years than in the QBO West years. So this is actually in favor of the further development of the MJO convection in the QBO East years. And although it is not directly related to the QBO variation, such kind of MJO scale tropopause instability may be indirectly influenced by the QBO phase, and that is a possible way how the QBO may influence the MJO. And there are so many debates between these two schools of the theories and all kinds of different other proposed theories. And one major factor that hindering our understanding of the proposed mechanism is that we really have very limited observations for data for our analysis. Like especially for the three-dimensional real analysis data, we only have several decades, and when you split into the QBO East years and QBO West years, we really don't have many MJO cases for our study. So you may think that maybe we can use the climate model to address this question, because for these climate models, we can have as many years as we want to investigate it in this long-term simulation. But the problem is that the MJO QBO connection is missing in climate models. Like in this figure, actually shows the MJO amplitude differences between the QBO East years and the QBO West years for the observation and for all the semi-sex climate models. And you can see that for all the semi-sex models, it cannot even simulate a stronger MJO in the QBO East year than in the QBO West year, not to mention to reach the difference amplitude magnitude of these kind of differences from the observation. So there are so many tries to address this question, to capture it in using the models. So the first try was in 2019, where Martin et al. They added the QBO T and U anomalies in the stratosphere for two MJO case handcuffs using the Wolf model, and they found that only by adding the temperature anomalies into the stratosphere, they can capture a weak MJO QBO connection. And this results actually largely supports the Toolbox instability theory. And in 2020, they did another experiment using the ECMWF prediction system, where they changed the initial stratospheric initial conditions by one arbitrarily selected QBO East and QBO West day. And they run a series of S2S prediction experiments. And again, they found a weak but captured MJO QBO connection, which is very promising. And in 2020, Beck et al. Did another experiment using the same Wolf model, but they targeted one MJO case in QBO Easterly winter, and then they reversed the low-pass filtered QBO variation in the stratosphere to mimic the QBO Westerly scenario. And again, they found a weak but captured MJO QBO connection. And after some diagnostic, they conclude that Toolbox instability theory is the responsible theory here. So for now, everything looks so good. It seems like we are only one step away to capture this kind of connection in the climate models. But then this happened in 2021. Martin et al. They used a NASA GIS GCM. They conducted a long-term simulation experiment, and where they nudged the lunar mean U and V in the stratosphere into these rounds to guarantee a very realistic QBO variation, including its temperature signal. But somehow it failed to capture the MJO QBO connection. And they tried several more GCMs, but they all failed to capture the MJO QBO connection in it. So this was very confusing to me, and I started to think about what might be wrong here. So I went back through the whole process again, and I found that they started with the original model, the Wolf model, and the way they introduced the QBO signal is by using a large scale forcing data, which is a prescribed fixed data on the top of the model, and the MJO QBO connection is captured here, which is good. And then they move to a forecast model, which is ECMWF model, and the QBO signal is introduced by interfering the stratospheric initial condition. But during the whole handcuff, the introduced QBO signal is allowed to evolve freely, and also the MJO QBO connection is captured here. Then, to me, it seems that they made a little bit jump. Not only they changed the model from a forecast model to a climate model, but they also changed how they introduce the QBO signal. Like in this work, they introduced the QBO signal by doing a zoonomy nudging, which means the introduced QBO signal is a fixed prescribed state, and it's not allowed to evolve freely. And every upon time, you cannot interfere the interactions between the MJO convection and the zoonomy flow. So I kind of wonder if like we use the same nudging strategy, but instead of using a climate model, but also using a forecast model, conducting the same experiment, whether we will see the MJO QBO connection here. Because if we still can see MJO QBO connection here, maybe if we fail to see MJO QBO connection here, maybe we should look more into the differences between the forecast model and the climate models here. And if we still can see MJO QBO connection here, that means that maybe how we introduce the QBO signal, whether it is free or fixed state, does not make any differences. So since we are going to conduct some experiment consuming some core hours on our machine, I really want to design my experiment in a more dedicated way so we can answer more questions. So there are two other questions I'm really interested in. The first is that where comes the QBO-MJO connection in the S2S prediction system? Why do we see it in this prediction system, but we didn't see it in the climate models? It is simply that it is possible that these prediction systems are simply maintaining a stronger MJO from the initial conditions in the QBO east layer than in the QBO west layers, or is it that there are indeed some correct model physics that in the prediction systems that allowing us to capture that? So to answer this question, I will select two MJO cases and run handcast experiment initiated in the QBO neutral winters. By selecting the MJO cases in the QBO neutral winters, I can guarantee that there's no QBO's influences on the MJO in the initial conditions. And by doing that, so all the responses of the MJO we see are due to the introduced QBO signals. And the second question is, which is more crucial to the MJO-QBO connection, the QBO wind shear or the QBO temperature profile? So I really want to revisit the Toolbox instability theory, because we see that although you get a very realistic QBO temperature in the GZM, still the QBO-MJO connection is missing there. So to address this question, I will add the Zoomer mean QBO T and U respectively into our model and see the MJO's responses. So yeah, and we decided to use the CESM2 Subseasonal prediction system to carry our experiment, which is an ensemble prediction system with 21 ensemble members. So for each selected MJO case, I will carry out a pre-control run, which is a totally free run without any nudging. And then for the selected variable, I will add the composited QBO anomaly from the observation to the states of the pre-control run and nudge it in the stratosphere only to generate the QBO easterly and QBO westerly runs. And also, I double the composited QBO anomaly from the observation to mimic the super QBO easterly run and super QBO westerly run. And these nudgings are done for temperature only, but leave the U untouched for QBO T free U experiment, and for the QBO U free T experiment, vice versa. And both U and T are added by these anomalies and are nudged in the Zoomer mean for the QBO UT experiment. And also, by the way, these nudging are only done in the stratosphere, but the troposphere is left untouched. So after finishing these all kinds of runs, I started to diagnose the model outputs. I started with the QBO T3U experiment, and I found somehow the QBO-MJO connection is captured for both two cases in the QBO T3U experiment. Here I show the predicted RMM and ROMI index evolution for the first case, case A, in QBO T3U experiment. And you can tell that in the first 2 weeks of the prediction or the handcast experiment, these runs with different QBO phases are really close to each other. But after week 2 to week 3, these different runs start to deviate from each other, with the super QBO easterly runs the strongest amplitude in RMM index and the ROMI index. But for the super QBO westerly runs, these runs with the blue colors are always the weakest in the RMM index and ROMI index. So that indicates that at least the MJO amplitude differences due to the different QBO phases is captured in by this setting. And then we investigated the eastward propagation of the predicted MJO event. Here are the Hofmuller diagrams of the equatorial predicted OIR anomalies. So the shadings are the differences between the QBO easterly and QBO westerly runs on the left, super QBO easterly and super QBO westerly runs on the right. And the lines here are the diagrams for the predicted OIR anomalies in the QBO westerly runs on the left and super QBO westerly runs on the right. So for the QBO runs in the QBO easterly years, the predicted MJO OIR actually gets amplified over the central western Pacific starting around day 28. And this actually helps the eastward propagation of the MJO convection. And if you look at the differences between the super QBO scenario, this kind of amplification is much more obvious with a greater amplitude, and it occurs much more earlier, around day 14. And the pattern clearly helps the eastward propagation of the predicted MJO convection. And that's for case A and in the QBO-T3U experiment. And a similar situation for the second MJO case, case B here. Also, the QBO-MJO connection is captured in the QBO-T3U experiment with the weakest predicted RMM and ROMI index amplitude for the super QBO West-D runs, and for the super QBO East-D runs, these two indices are the strongest. And also the amplification and further eastward propagation of the predicted MJO ORR convection is evident in the super QBO East-D runs and QBO East-D runs. So by so far, we conclude that the MJO QBO connection is captured in the QBO T3U experiment. That is by not in the QBO temperature only, but setting the lunar wind to be free. So how about the situations in other two sets of experiment? So to measure that, we use three different methods to measure the predicted MJO amplitude. That is the ORR anomalies predicted during the week 3 to 4 and averaged over the central western Pacific. And we also use the RMM amplitude and ROMR amplitude average between weeks 3 and 4 to measure the predicted MJO amplitude. So on the top row, we really would like to see that the predicted MJO ORR is more negative in the super QBO East-D runs and also in the super QBO East-D runs. That means more blue in the first row. And at the bottom two rows, we really want to see more red, that is stronger index amplitude for the predicted MJO. And we found for both case A and case B, only the QBO T3U experiment could capture all these three correct responses for both two cases. For other two sets of experiment, they could capture more negative, that means stronger convection over the central western Pacific. However, the problem is that the amplification of the convection is not in the MJO scale, because we see very weak or even opposite sign of the RMM amplitude and the ROMI amplitude in the QBO runs or in the super QBO runs. So by so far, we conclude that the MJO QBO connection is captured and only captured by the QBO T3U experiment. Does it indicate that the QBO temperature is very important to capture for the MJO QBO connection? But let's not jump to our conclusions too fast. So we start to check the lunar mean temperature and the U anomalies in the QBO East-DS and QBO West-DS from the observation and from these three sets of experiment. So here the shadings are the temperature differences and the lines are the lunar wind differences. And we can see that first thing we notice that either you nudge temperature only or nudge lunar wind only, the other variable, the correct responses of the other variable is somehow naturally popped out. And we think that this is probably due to the fact that the model want to maintain the geostrophic balance between the U and T. So in conclusion, like for three different sets of experiment, we all see such kind of cooling around the 100 hectopascal, but only the QBO T3U experiment is capturing the MJO QBO connection. So we think that lunar mean Tropopause instability cannot fully explain the captured MJO QBO connection. There must be something unique in the QBO T3U experiment that is allowing it to capture the MJO QBO connection. And one unique thing we notice is that although we all get this kind of wind shear around 50 hectopascal for all three sets of experiment, the wind shear we get in the QBO T3U experiment are allowed to evolve freely. It's natural responses like from the model in response to the temperature anomaly nudged in. But for the QBO-U3T and QBO-UT experiment, such kind of vertical wind shear is generated by the nudging. So it is a fixed state, and every upon time you kind of interfere the interactions between these kind of vertical wind shear and MJO convection. So we do think that the freely evolving QBO-U wind shear might be crucial to capture the MJO-QBO connection. So remember, we talked about two types of tropopause instability. One is the Zuno mean tropopause instability we already investigated here. And the other type of tropopause instability is the so-called MJO scale tropopause instability. To investigate its role in capturing the MJO-QBO connection in the QBO-T3U experiment, we did a very simple diagnostic. So here, the x-axis is actually the MJO tropopause stability measured by the temperature differences between the 100 and 200 hectopascal, and it is averaged around the MJO convection. And the y-axis is actually the MJO amplitude, which is by the Romy OLR, also averaged around the MJO convection. And each dot here actually is one single ensemble member for our experiment from different phase of the QBO, different runs with different QBO phases indicated by the different colors here. So this is for the QBO-T3U experiment, QBO-U3T experiment, and QBO-UT experiment for case A on the top row and case B at the bottom row. So by eye examination, at least you can tell that the distribution of these dots does not change much among three different sets of experiment for both case A and case B. And in fact, the robust positive correlation between these two variables are evident for all three sets of experiments for both case A and case B. And if the MJO tropopause instability is the responsible theory to capture the MJO-QBO connection, now we illustrate that at least for QBO-U3T and QBO-UT experiments, these two experiments is capable to capture this kind of relationship, but somehow they failed to capture the MJO-QBO connection. So we think, although these two variables are correlated with each other in three sets of experiment, the MJO tropopause instability is not the causality of the predicted MJO amplitude changes with different QBO phases. So we think, the MJO scale tropopause instability is not responsible to capture the MJO-QBO connection in the QBO-T3U experiment. And finally, some summary. So we conducted some experiment with the Zuno mean QBO-U and T nudged into two MJO case hindcast in the QBO neutral winters. And we found that only by nudging the QBO temperature, but setting the Zuno wind free, can we capture the QBO-MJO connection. And we show that the prediction system had the potential to capture the QBO-MJO connection, even without the help from the initial conditions, because these two MJO cases are selected from the QBO neutral winters. And we investigated the role of the tropopause instability theory, and at least it alone cannot fully explain the captured connection. And for future work, we really want to see if we apply the same nudging strategy for the climate models and conduct these long-term unenergized simulations, can we still capture the MJO-QBO connection as we see in the QBO-T3U experiment? And another question we're really interested in is that what is also responsible other than the tropopause instability for the captured QBO-T3U experiment? Since we see that the freely evolving U is very crucial to capture that, if there might be any possible theories related to the interaction between the waves and Zuno mean flow that is allowing the model to capture the MJO-QBO connection, and we are still investigating that. And yeah, if you have any ideas or suggestions on how to diagnose that, especially on the role of this interaction of the high frequency waves and the Zuno mean flow, and we are more than happy to take that. Yeah, and yeah, that's the end of my presentation. Thanks.
Great, thank you, Kai. Well, we do have a couple of minutes for questions here. I do see one's in the discussion document here, and I'll just go ahead and read that to you. So So slide 10 through 14, you showed the MJO difference by QBO is simulated mainly in later MJO phases, phases 6 through 8. Isn't the largest observed QBO-MJO signal over the maritime continent phase 2 to 4?
Yeah, so in observation, the largest differences are mainly over the phase 4 and 5 and 6, maybe. But like if you check our experiment, yeah, for the first case, we initiate our handcast in phase 2, and we think that allows the MJO convection to feel the influences of the QBO early enough. And we do see this kind of responses occurs much earlier, like around day 14 for the super QBO scenario. And part of these influences are over the maritime continent. But for the second MJO case, we have to start it a little bit later when it's already over the boundary of phase 3 and phase 4. So my impression is that this actually does not allow much of the time for the predicted MJO to feel the influences of the QBO when it's over the maritime continent region. So for the second MJO case, it's not that obvious like responses over the maritime continent. And another possible question is, possible reason for that is that we did some super QBO runs and the QBO runs. Here in the zonal wind profiles, the dashed lines are the wind shear for the super QBO scenarios. And for the QBO T3U experiment, you see that by only by doubling the QBO temperature anomalies, we should get a reasonable magnitude of the vertical wind shear related to QBO, especially around the 50 hectopascal. So we really think if the zonal wind shear is crucial here, for the QBO runs, which are the solid line here, solid right line here, the wind shear is not strong enough to induce such kind of strong responses over the maritime continent. But if you check the situations in the super QBO runs, and you will definitely see some responses over the maritime continent around day 14. Yeah.
Okay, thank you. Any other questions from anybody else? Well, we have 1 or 2 minutes left.
This is DK. Can you hear me?
Yeah.
Yeah. So Kai, can you do you mind providing the answers in the document document we are providing? That would be great.
Sorry, can you say that again?
Yeah. Can you answer the questions in the document?
In the document? Okay. Yeah. Sorry, I can't see that document. Somehow I can't get access to it. Maybe someone can read it for me. Sorry.
It was actually the one that I just read, and I think wanted just text put into the document answering it for the person who asked the question. So we can send you. I'll give you access to that document if you don't have that yet, and you can add that when we're done here.
That'd be great. Thank you.
Okay, so we are about out of time, so I want to thank everyone for showing up, and I want to especially thank all 3 speakers today for both the presentations. And once again, make a plea if you have results, anything you'd like to share, go to the webinar website and fill out the form and request a time. We would love to hear from you. And thank you, and everyone have a great day.
Thank you.
Thank you.